Hello everybody, today we shall solve this problem 9 and give some hints about next problem 10. So here we need to find the points on the surface of the cube from which its diagonal can be seen at the smallest angle. So let's start. We shall first give some hints and then we shall give a precise proof. So I shall try to draw approximately one cube. Okay, it's just a sketch, but it will be enough for our purpose. Okay, I shall draw in red one diagonal. So this is diagonal of the cube. And actually we are going to prove that the smallest angle is the right angle. So what does it mean to see the diagonal from some point? So we take a point on the surface of the cube, and if we join with the edges of the diagonal, this is an angle under which we see the diagonal of the cube. And actually we prove that the smallest angle is a right angle, which can be obtained if we take just a vertex of the cube. So if we take one vertex of the cube, for example, like this, then if we join here and here, it's actually obviously that this will be the right angle, that we have two perpendicular lines here. So this is the right angle, or 90 degrees. Okay, so we will prove that any other angle is actually greater than 19 degrees, or obtuse angle. So this one will be obtuse angle. So we will prove that actually it is not possible to obtain a pointed angle. First some prerequisites. So if we have a circle, and this is a parameter, this is the center of the circle, and if we take any point on the edge, on this circumference, we will obtain actually this parameter can be seen under a right angle. So this is right angle. So this is the famous Thales theorem, which is the special case of so-called theorem about parameter angle, that this parameter angle is always half of the central angle. Here central angle is this one, which is actually 180 degrees, and this parameter angle is 90 degrees, but it is actually obvious in a general sense. Even this line is not through the center of the circle. So this is the Thales theorem, and from this Thales theorem we can conclude the following. If we have again the same circle, the similar situation. But if we take the point outside of the circle, then, and if we join with these points, this will always be less than a right angle, so a pointed angle will be obtained here. This can easily be seen if we take one of those lines will certainly intersect the circle here, and if we join here according to Taylor's theorem, this is a right angle, and it is known that this angle here is the sum of this and this angle as an outside angle of this triangle ABC. So outside angle of the triangle is the sum of the other two angles, this angle and this angle in the triangle. So for the point outside of the circle, this will be a pointed angle which is less than right angle, less than 90 degrees. And this will now use to show that it is not possible that this angle here, let us call it alpha, that it is not possible that this angle be a pointed angle, less than right angle, and in that way we will prove that this 90 degrees is the smallest value for the desired angle. So how we point this? Actually, let me call this point A and this point B. So we will take a circle where this AB is actually a double radius. So here AB. So this is the center of the circle. So this is actually a diagonal of the cube. So the radius of this circle is d over 2, d2 here, d over 2 here. And so if this is the point C, and if we assume that this alpha is less than right angle, that it is a pointed angle, then C actually will be outside this circle. So this C should certainly be outside of this circle. And what we get here that the distance from S to C, that this distance, let me call it x, is actually greater than the radius of this circle, or actually greater than d over 2. And that is not possible. So this S is in the center of the cube, and there are no points on the surface of the cube which are at the distance greater than d over 2. d over 2 is the greatest distance. It happens actually in the vertices of the cube. Actually, we can take the sphere with the center in S, which is passing through all vertices of the cube, and the radius is actually d over 2, and the whole cube is inside that sphere, that ball. So there are certainly no points on the surface of the cube which are outside that ball. So there are certainly no points at distance greater of d over 2 from the center of the cube. And so this is actually the end of the proof. Sorry, I understand that my English is not completely clear, at some points of my presentation, but I hope that this simple proof is actually clear, because it is really a simple proof, and actually we use actually nothing than Thales theorem that this angle here is the right angle for any point. If we take another point here, we again obtain the right angle here. This is the only let me call non-trivial fact that we are using here, and also some points about some facts about angles of the triangle. We actually know that if we have triangle, then with alpha, beta, and gamma be angles of the triangle, then alpha plus beta plus gamma is 2 right angles, or 180 degrees. And actually, if we take outside angle of the triangle, this particular one here together with beta is again 180 degrees, and actually it is from this relation, this angle here is actually equal alpha plus gamma. And so we use this here, that this right angle is the sum of this angle here and this angle here, and thus we prove that this is a less than right angle, that for a point outside of the circle we have a pointed angle actually. Okay, so a few points sorry, I didn't prepare myself for erasing this, but never mind. I will have enough space here. So a few points about next problem, problem 10, which actually I am not sure that I will be able to prove. It is not clear for me how to prove this, but I have some ideas what should be done. So we have a convex polygon such that no triangle of area 1 can be placed inside it. And we need to prove that this polygon can be placed in a bigger triangle of area 4, which is so 4 times bigger. So what is actually sorry, just me prepare things. So what is actually the problem here? So if we have some convex polygon, if we take any triangle which is inside the polygon, we know that this area here is at most 1, so less or equal to 1, and we need to prove that we can place this whole polygon inside another bigger triangle, which has area of 4. So that area of 4 is enough to cover this polygon with a triangle. So what is actually the idea? The idea is to replace somehow to connect this polygon with a circle. So what we have in the case of the circle. So in the case of the circle, we have that the biggest possible triangle Sorry, I wanted to change the color to be similar to the previous picture. So the biggest possible triangle which can be inscribed in the circle is actually a triangle with isocycle, a triangle, so with all equal sides. And the smallest triangle which in which can be inscribed a circle is actually again a triangle with all equal sides. Let me call them B. And we actually know that B is equal to 2A because when we have a triangle with all equal sides, then we know the connection between radius of inscribed and circumscribed circle. So if this is the radius R and this is the radius big R, we know that actually big R is 2 times small r. So from this we also know that in this case actually B is equal to 2A. So we know that if this small triangle has area P, then the bigger triangle has area 4P because sides are double in size. So that is the idea, somehow to connect this special case with the case of general convex polygon. But it's at this point I don't know how to solve it. So it's a difficult, at least for me, it's a difficult problem. But you already know I pick not the problems which I know how to solve, but somehow randomly from one of my collection of mathematical problems, I pick them randomly and to publish on my site ivik.ultimaiq.net, where you can find those problems and try to solve them. And I shall continue to publish and solve them at some pace, I hope pretty much regularly, although at this point I really have many obligations, but hopefully it will change in the future. So maybe I will continue at some slower pace for now, but actually I hope that we will grow as a channel and that I will also have more free time in the future. So thank you very much for watching and enjoy in mathematics. I hope that I will be able to present some of my knowledge to all who are interested in learning some mathematics, no matter for fun or for a school or for a job or for anything in life. We never know what will be need, what we will need from mathematics in our life. Mathematics is pretty much abstract and general, and I can agree that many things from mathematics we will maybe never need in some stronger sense, but we actually grow as human beings when we are doing anything that is good, and mathematics is actually mathematics can be good as anything else if it is done with good purpose. So See you next time. Bye bye.